Hello, my name is Timotei Ardelean, and I will present our work on high-fidelity, zero-shot texture anomaly localization using feature correspondence analysis. First of all, what is anomaly localization? As part of the broader topic of anomaly detection, this task refers to identifying unnatural, abnormal, and unlikely items in a collection. More specifically, the task is to find the anomalous regions, if any, in a set of images. These anomalies can take various forms depending on the type of object or material that we are interested in. For example, cuts and snags in textiles, scratches on wood, or a crack in a tile. Detecting and localizing anomalies is an essential part of quality control and industrial inspection, and solving this task more accurately can bring significant benefits. In this project, we approach the zero-shot setting of the anomaly detection problem. One of the most significant challenges in anomaly detection is data acquisition and labeling. It is generally hard, or even impossible, to obtain a set of images that cover all possible anomalies and annotate them. That is why the prevalent paradigm for anomaly localization nowadays is to approach the problem in a one-class classification setting. That is, to assume the existence of a curated set of normal images and use it as a reference to determine if a new sample is anomalous. Several mainstream approaches are in this category, such as SPADE, patchcore, and coupled hypersphere-based feature adaptation. However, in certain cases, such a curated set of normal images may not be available or may be costly to produce. In this case, zero-shot methods that detect and localize anomalies from a single image are paramount. We identify two fundamentally distinct classes of methods that have been proposed for zero-shot anomaly localization. One approach is to use a large pre-trained network, such as a visual language foundation model, which practically learns the concept of anomaly through large-scale training. The second category identifies anomalies by considering the image as a collection of overlapping patches that should normally have a similar distribution. By comparing the statistics of the image patches, anomalies are found by pinpointing outliers. Notably, by design, this class of methods can only be applied to textures, which are largely stationary. Our solution to zero-shot anomaly localization belongs to this category. In our paper, we formulate a framework for this second class of methods based on stationarity analysis. Essentially, we describe the anomaly score A at a certain position xy in terms of three components: feature extraction, patch statistics comparison, and reference selection. The first component extracts information from the input image into feature maps and can consist of, for example, a steerable feature pyramid, loss texture energy measure, or intermediate features from a pre-trained convolutional neural network. The patch statistics comparison is the heart of the pipeline, dictating how to analyze the distribution of each patch with respect to the global statistics in the image. The reference selection component determines how the global information is represented. For example, one can take random samples or average all patches to obtain such a global reference. The generic character of the formulation allows prior work, such as the texture stationarization paper of Moritz et al. And the zero-shot method of Aota et al. To be expressed in this framework with different ways to implement the three components. In our work, we explore this design space and propose a novel algorithm for the patch statistic comparison step, which significantly improves the fidelity of anomaly localization. Our algorithm, named Feature Correspondence Analysis, or FCA, works as follows. To obtain the anomaly score for a pixel location in the feature maps, we will look at all neighboring patches of a fixed window size. Next, the features inside each patch are viewed as a distribution. We flatten the patches and sort the values, essentially obtaining a cumulative distribution function. The distribution of each patch is then compared to a global reference. In our case, this is computed as the optimal reference, which minimizes the overall anomaly score across the entire image. This is in fact easy to compute by taking the median over the features from all patches at each sorted position individually. We then compare each distribution to the reference by taking the absolute difference between elements of corresponding rank in sorted order. Afterward, we undo the sorting and remap each pixel level error to the corresponding position in the patch. Finally, The patches are folded back so that the anomaly score at a particular location is the average of the error contributions in each of the surrounding patches. An intuitive option for the patch statistics comparison component of the pipeline is to use histograms and compute the Wasserstein distance between distributions. We show here the advantage of our algorithm on 2 synthetic and 2 real images from the MPTech dataset. Due to the holistic comparison of distributions implied by the histogram method, it is impossible to get satisfactory results on the second synthetic example, regardless of the patch size t used. On the right-hand side, we perform the direct comparison between our method and histograms on real images. Similarly, our FCA yields a more precise localization and fewer false positives. We present here our results, comparing our approach with state-of-the-art zero-shot anomaly detection methods. The method of Aota et al. Is a stationarity-based method, whereas AprilGAN is based on a language visual model. We also include the combination of our method with k-nearest neighbors-based reference selection. You can see that our anomaly maps have higher fidelity, being closer to the human perception of anomalies. The same observations can be made about the thresholded anomaly maps. We show here the binary separation of anomalies illustrated using contours. Our method's contours are both tight and complete. In that sense, we consider our method to have higher fidelity than previous methods. The numerical evaluation, in terms of the usual metrics, robustly confirms the advantages of the proposed approach. Notably, on textures, we even outperform methods such as patchcore, which make use of a curated set of normal images. For completeness, we also evaluate methods that address related tasks, such as saliency detection and weathering estimation. We analyze our approach in different combinations of patch statistics comparison and reference selection in terms of computational complexity. While our method is more involved and thus slower compared to simple approaches, such as using histograms, it scales better at high resolution compared to the method of Aota et al., which computes the k-nearest neighbors of each patch. In this figure, you can observe the results of our design space exploration. Namely, we analyze how various feature extractors and the methods for comparing patch statistics affect performance. Notably, the improvement brought by our FCA over trivial alternatives is consistent across several types of features, speaking to the robustness of our approach. To summarize, our contributions are as follows. We introduced a conceptual framework for detecting anomalies in textures consisting of 3 components: feature extraction, patch statistics comparison, and reference selection. We propose a novel method for comparing patch statistics with higher fidelity, which we name FCA. And finally, we thoroughly explore the design space, highlighting the importance of each component of the pipeline. Thank you for your attention.